Good morning, guys. My name is Adrian Quesada. This is my colleague,
Alan Adrian.
and we're going to be talking to you guys about our 64-bit processor, the A² Pro XIV, and it's going to be brought to you guys by VQ Incorporated, which is our company name. All right, so on our agenda today, we're going to be talking a little bit about the information of our company and a little bit of background of our processor. We're going to jump into the baseline overview, the design of our processor, and give you guys some examples, followed by a Q&A session. All right, so give us 1 second. I think one of our slides got switched off. Good, yeah. Because I'm supposed to. All right, so let's just talk about our processor design. Sorry about that, guys. So it follows a Harvard architecture, and that involves a CPU communicating with two separate memory modules. So one for the instructions and the other for our data. It encompasses the RISC philosophy, which is using load and stores to access our memory, and it's used in little Indian format, as you can see the example here. So the lower 32 bits are going to be sent to the lower address, which follows then the upper 32 bits are going to be sent off to the address right above that one. All right, so for our registers, we have a 32 64-bit integer register. The same thing for our floating point register. We have 32-bit instruction pointer register, a 32-bit stack pointer register, and our stack is based on pre-dec post-inc. So pre-dec for our push and posting for our pop. We have an 11-bit wide flag register, 4 of which are our integer flags. One's going to be our interrupt flag, and we have 6 of our floating point flags. Our addressing mode encompasses these 3: our register addressing, immediate addressing, and indirect addressing. And here's our codes. So our instruction formatting is pretty much our triple operations, doubles, singles, calls, jumps, flags, immediates, and how we encompass these are these little diagrams that show how we went through, labels them out pretty nicely, knowing which opcodes go for which instruction and their abbreviations, and there's 80 of which we did for our processor. Here's the second. So now we're going to be moving on into our block diagrams. This is our top level. It's going to be the CPU test module. So in here we have the control unit and the CPU execution unit. And this one is going to be talking to our memory, and it's going to be talking to our I/O. So the I/O is the one that has the interrupt request that sends it over to the CPU, and this one returns with an acknowledge. They get the same data bus from the data and the address. Jumping into the CPU, you can see our control unit and all of the control signals that go over to the CPU. And the one that we had, the only one that went from the CPU back over to the CU64 was our flags out. That goes back into flags in. And down here you can see how it's going to be interfacing with our memory modules and our I/O. Now jumping into the integer data path, it's pretty much the same as the one we had in the baseline. The only thing we added over here was a temporary register, which would allow us to use a manipulation with the mugs for doing the exchange instruction.
The floating point data path, we also added some of the we incorporated this FS mux. This was something that allowed us to bring in some of the data from if we needed to add onto it, and we'll actually use it in one of the instructions later. So just to show you that this is one of the things we did add to the baseline floating point integer data path. This is our BIU. We also added some of the muxes going into the instruction pointer because we needed to be able to load 3FF for certain things. We needed to also add the relative addresses, so wherever the IP was, and then add it back onto, use the adder to add whatever instruction from the 23 to 0, I think that was. And then another one was also to be able to read the read buff. So we're able to save states and just from the read buff go directly into the IP. One of the things that we did different than other people did was that we added our MUX to be able to add, if we had data coming out from our read buffs, some people in their integer data path, they went ahead and put another MUX inside their integer data path. Well, we did it outside, just right here. And that was our DS MUX. The DS MUX is controlled by that guy. Oops. These are the instruction set examples that we're going to go through right now to show you the operation of the process, right? So the first one is the triple operand instruction, which is pretty easy. It's a simple one. It's just the opcode, which is 8 bits, source register 1 and 2, and then the destination register is where it's going. Then we're going to go into our integer data path. That's where all the instructions, that's where these guys pretty much happen, the triple operand. So one of the things, first off, wherever the R address is pointing to, that data goes into the R side of the ALU. Wherever the S address is pointing to, the source 2 register, that goes into the S MUX, and then that goes into the ALU on the S side. Comes out of there, whatever, the operation here would be R plus S. Comes out here, out of the Y MUX. And we go into our Y, again, this MUX that we added in here was because of this register. This register gets written on every clock cycle, so the only time that it actually goes into the register file was in exchange is actually used. And that was for the exchange instructions, so we can just swap them over. Or we can hold this register with whatever we're writing for that guy. So but here we're not using it, but we do go ahead and go through that MUX. We're allowed to with the data from Y MUX. And then based on the W address, which is the write address, we went ahead and wrote it into the register file. Double operand instruction is pretty much the same format, just the only difference was that certain instructions only used the destination and one of the source registers. We still have the opcode. And then these are the key components and what happens. Previously, the triple operand only used the integer data path, but these instructions, like the output, took a register, something inside, data inside of the integer data path, and that's put out on that's the destination of where it's going. So that goes into the memory address. So saying, okay, we need to put that eventually into here. So this is where it's going, and then the ALU out tells us our source 1. That's the only two that are using. So first, the WR buff gets loaded, and then there's the address of that one. We increment the memory, the MAR on that one also, and we output the WR buff 1, which is the upper bit, upper most significant 32. And that gets both written for the output. Oops.
All right, so we're going to be jumping over to the single operand instructions, which you're most likely just using the source 1 register. And we're going to be performing a pop. So pretty much on the first state, you're going to be loading, you're going to be decrementing the SP, but it won't happen until the next clock cycle. And you're going to be going into the data memory because you're going to be wanting to pop, so you're going to want to read. And at the same time, you're going to be grabbing whatever value in small Indian form in Little Indian. So you're going to be grabbing the lower 32 bits, and you're going to be loading those first. On the second state, you're going to be doing the same thing again. Now you have decremented, so now you're at the one right on top of that. You're going to be trying to read the upper 32 bits, and that happens here. So now officially you have both the read buff 1 and read buff 0 loaded. And now in the third state, you're going to be writing it back to the register destination. going into the conditional jumps for like jump of carry. On this one, we're just gonna assume that a carry was set. As you can see by our index of 4 right here. And the coding that we used for this is if the index 4 has a 1, then you're gonna be choosing which IP select you're gonna be grabbing from, either from the read plus 0, the 3FF, or if you're gonna be adding what the jump value to the IP is, and you have to make sure that the IP load is actually enabled so you can load onto that register. And this pretty much happens on one state.
What's the stop? $sign stop.
Oh, we use a lot of these stops in between, so we could kind of see where we were at when we were doing our decode. So
that was deleted, but I think this was previous code. So.
Yeah, but that's kind of so we could see, so like our breakpoints kind of thing.
But your processor doesn't have those breakpoints, right? You pull them out later?
Yeah,
Oh, yeah.
we did afterwards. And so pretty much now we're going to be talking about the call instruction. So this one encompasses a little bit more of the BIU. On this one, on the first state, you're pretty much going to be writing on, so kind of like a push.
We had 2 calls, right? Which call are we looking at?
Sorry, relative.
Okay.
Yes, relative. So this one's a relative, so pretty much you're going to be trying to save the value of your IP, because you're going to want to come back to that afterwards. So on the first state, you're pretty much handling all of these things to go on. So you're grabbing the sign extension 23 0, and you're adding that to the value of the IP. You got to make sure that your mux loads are enabled, so then you're able to use this mux, and you're going to be setting it at 0, so you know that you're going to be grabbing the IP. You're also going to be loading the right buff, the lower part and the higher part, the upper bit, the 32-bit most significant and the least significant. And then on the higher part of it, for the 63 to the 32, you're going to be grabbing just the 32 bits of 0, because you're only grabbing the IP that you want to be storing onto the stack. And you have to make sure that your stack pointer is going to be decremented for the next time that you go around to go on to the next part. On the second state, that's when you're actually going into the data memory and going to the specific location of where you're storing the lower part to. On the third part, that's when you're going to be loading the upper bit, which is the 32 bits of zeros.
So you're just pushing the zeros?
Yeah, because we want to keep the 64-bit format
for calls though, because you're only pushing 32 bits, I thought. But you went ahead and pushed 64 bits anyway?
So it was call.
So you had to push the program counter.
Yes.
Oh, which is the only 32 bits as opposed to 64.
Yeah. Unless you had a kind of a universal push routine that you use for whatever.
Mm-hmm.
No, we didn't. So that's probably, that's actually a mistake.
Because the return is just going to pop off whatever. Now it has to pop off the 0, throw it away, then pop again and put it in the PC IP.
Yes.
Is that the way you did it?
No, ours, that was just a mistake.
Yeah, when we were doing it, it made sense when we were writing it down and going through our steps. But right now looking back to it, yeah, that was a mistake on our part.
But did you push those upper 32 bits to 0?
No.
No.
Okay, you didn't do that. Okay.
No.
Okay.
Okay. So now we're going to jump over to the flash processor set of carry. And pretty much on this one, we're not really messing with the BIU and other stuff. You're just focusing on the software part. So if it starts off at the index 4 to 0, you're gonna, in order to set the carry flag, if you just wanted to manually set it, you just go to your next state and set your next state to be what the present state is, and or it with the same thing of 11 bits, but make sure that the 4th index is going to be set. And pretty much afterwards, this is what happens.
Okay, so the immediate operand instruction is this guy right here, where this was a difference where we needed to, in one of the sign extensions, we sign extended 23 to 0, but this one we had to have another sign extend in our BIU so that we can only sign extend the 15.8 for these instructions.
Mhm.
So the sub I instruction basically takes in the instruction will have the actual value, so that'll get sign extended like I showed earlier, or I said earlier. And that value, based on the R address, you have your source one, that's one of the values. Then you bring in your, on these SMUX right here, you bring in the value, sign extended 15.8, and that's what we're actually subtracting R and S. So R gets subtracted with the immediate value of 15.8, or now it's 64.5. You get the value that then comes out goes through a WR mux once again, and based on the W address that we get over here, is the right address of where it's going to be stored in that registry file. The floating point instruction, which was an OR high, floating point OR high, basically the triple operand format. The difference here was that whatever the instruction, the floating point OR high basically would OR the high bit, higher bit of a value onto the 32-bit, 64-bit value. It would OR the 32 most significant bits based on whatever the instruction. It would be in 15.8, so we we take that and put that into the rebuff one, and then now we have that in there. And rebuff 0 also gets load Z was a control signal I used to basically reset it. So like that, it would be all zeros because we need that to be all zeros, not just whatever is in there at the moment. So we have the upper 32 bits, and then the lower 32 bits are all zeros. That gets pushed in there, and that gets brought in on our FPN. And then, like I said earlier, it gets sent up to that FS mux, and the FS select is now selected to take an input from that value, so we can use that or the original R address, the source one, with that value now, so we can OR the upper 32 bits onto that, R or S, we add that, and then that goes back into that original R address. And at this point, we're opening it up for a question and answer.
So do you guys have future plans?
We thought of, there was, everybody was doing a barrel shifter that's pretty common. One of the things we wanted to get into was digital signal processing, but that seemed pretty complicated. We had enough problems with our baseline, so we kind of just stuck there. But in the future, we do want to take it further
And expand.
Good job. That's great.
Thank you.
Yeah, thank you.